Something is shifting beneath Yellowstone National Park, and the latest data is forcing a closer look at what lies below one of the most closely monitored volcanic systems on Earth. Not because of a single dramatic event, not because of a sudden surge of earthquakes or deformation, but because the picture of the subsurface itself is becoming sharper and more complex. What once appeared as a distant, poorly defined body of molten rock is now resolving into something far more structured and dynamic. How close is molten material to the surface, really? What does closer mean in a system that does not behave like a single magma chamber? And how does new imaging change the understanding of risk in a place already known for its immense geothermal energy? Recent advances in seismic imaging and integrated geophysical modelling, particularly research directions emerging through the years 2025 and 2026, are refining the understanding of Yellowstone's magma system. These developments are not rooted in speculation, but in increasingly detailed observations derived from seismic wave behaviour, ground deformation measurements, and electromagnetic surveys. The result is not a simple confirmation of magma rising toward the surface, but a more nuanced revelation. Molten material exists at multiple depths, and in some regions, portions of that system appear to extend much closer to the surface than previously mapped with this level of clarity. Earlier models often described Yellowstone as having two primary magma reservoirs, a deeper basaltic source located roughly 20 to 50 kilometres, or 12 to 31 miles, below the surface, and a shallower rhyolitic chamber at depths between about 5 and 15 kilometres, or 3 to 9 miles. These estimates were based on broader seismic interpretations that, while useful, lacked the resolution now achievable with modern computational techniques and denser seismic networks. What is emerging instead is a vertically connected system composed of multiple zones of partial melt, storage regions, and pathways through which magma and heat migrate over time. The concept of a single, large molten chamber dominating the subsurface is being replaced by what scientists describe as a mush system. In this context, magma is not uniformly liquid, but exists as a mixture of solid crystals and molten material. The proportion of melt within this mixture, referred to as melt fraction, is a critical factor. Recent studies indicate that Yellowstone's melt fraction ranges approximately from 6% to 28% in various zones. This means that in many areas the subsurface is not a vast pool of liquid magma, but rather a partially molten framework where solid and liquid coexist. This distinction is essential when considering the idea of magma being closer than ever. The phrase does not imply that a fully molten chamber is pressing upward toward the surface in a direct or imminent sense. Instead, it reflects the improved ability to detect and map regions where partial melt exists at shallower depths than previously resolved. In some areas beneath Yellowstone, the uppermost portions of this system are now being imaged at depths of approximately 2 to 4 kilometres, or about 1 to 2.5 miles below the surface. At those depths, the environment is still far from what would be required for an eruption. Pressure, temperature, and the mechanical properties of the overlying rock all play a role in determining whether magma can ascend further. The presence of partial melt at shallow levels does, however, influence the behaviour of the geothermal system above it. Yellowstone's famous geysers, hot springs and fumaroles are all expressions of heat moving upward through the crust, driven by the underlying magma system. Changes in the distribution or connectivity of these shallow melt zones can alter how heat and fluids circulate, sometimes producing subtle shifts in surface activity. Seismic tomography has been central to these discoveries. By analyzing how seismic waves travel through the Earth, researchers can identify variations in rock properties. Areas containing melt tend to slow down certain types of seismic waves, creating detectable anomalies. With improved instrumentation and data processing, these anomalies can now be mapped with greater precision, revealing smaller-scale features that were previously indistinguishable. Instead of a single blurred region, the subsurface appears as a layered and interconnected structure, with zones of differing melt content and temperature. Another key component of the updated understanding comes from integrating multiple data sources. Ground deformation measurements, often obtained through satellite-based interferometric synthetic aperture radar, provide information about how the surface is moving over time. Uplift and subsidence patterns can indicate changes in pressure within the subsurface. When combined with seismic data, these measurements help to constrain models of where magma or fluids are accumulating or migrating. Electromagnetic methods add yet another layer of detail. These techniques measure the electrical conductivity of subsurface materials, which is influenced by temperature, fluid content, and the presence of melt. Regions with higher melt fractions or hydrothermal fluids tend to be more conductive, allowing researchers to identify zones that may not produce strong seismic signals alone. By combining these approaches, the resulting models are more robust and less reliant on any single line of evidence. The idea of deep recharge remains a central element of the system. Beneath the shallower zones lies a deeper source of magma, originating from mantle processes that feed the entire volcanic complex. This deeper input does not rise directly to the surface in a continuous stream. Instead, it supplies heat and material that accumulate in mid-crustal storage zones. From there, magma can evolve chemically and physically, becoming more silicic and viscous as it interacts with surrounding rock. Over time, portions of this material may migrate upward into shallower regions, contributing to the layered structure now being observed. This multi-level storage system introduces a temporal dimension as well. Magma does not move upward in a simple linear fashion. It can stall, crystallize, remobilize, and migrate laterally as well as vertically. The presence of melt at shallow depths today does not necessarily mean it arrived there recently. Some of these zones may have existed for extended periods, maintained by a balance between heat input from below and cooling from above. The improved imaging simply allows these features to be seen more clearly. In practical terms, the detection of shallow melt zones at depths of 2 to 4 kilometers refines hazard assessments without fundamentally altering them. The conditions required for an eruption involve more than just the presence of melt. There must be sufficient melt volume, connectivity between melt regions, and a pathway for ascent. Additionally, the pressure within the system must overcome the strength of the overlying rock. Current observations indicate that while melt is present at multiple levels, the system remains largely in a state where these conditions are not met simultaneously. Seismicity provides another important piece of the puzzle. Yellowstone experiences frequent small earthquakes, typically associated with the movement of fluids and the adjustment of stresses within the crust. These events are closely monitored for patterns that might indicate changes in the magma system. While earthquake swarms can occur, they have not shown a consistent trend toward shallower depths that would suggest a direct upward migration of magma on a scale associated with eruptive activity. Instead, they often reflect localized processes within the broader system. Hydrothermal activity, visible at the surface, is also influenced by the distribution of heat below. Variations in geyser eruption intervals, changes in hot spring temperatures, and shifts in gas emissions can all provide indirect clues about subsurface conditions. However, these signals are influenced by complex interactions between water, rock, and heat, making them difficult to interpret in isolation. The integration of these observations with geophysical models helps to place them in context, linking surface behavior to deeper processes. The evolving picture of Yellowstone's magma system underscores the importance of resolution in geoscience. As methods improve, features that were once inferred indirectly can be observed more directly. This does not necessarily indicate that the system itself is changing rapidly. Rather, the understanding of it is becoming more detailed. The phrase "closer than ever" reflects this shift in perspective as much as it does any physical change in the position of melt within the crust. At the same time, the presence of shallow melt zones highlights the dynamic nature of the system. Even without leading to eruption, the movement and distribution of magma influence the thermal and mechanical state of the crust. This, in turn, affects everything from ground deformation to hydrothermal circulation. The interplay between these factors creates a system that is constantly evolving, even if those changes occur over timescales that are long compared to human observation. The refinement of Yellowstone's subsurface structure is also changing how temporal patterns are interpreted, particularly in relation to uplift and subsidence cycles that have been observed for decades. Beneath Yellowstone National Park, the ground does not remain static. It rises and falls over periods spanning years to decades, sometimes by several centimeters per year, occasionally reaching rates equivalent to about 7 centimeters annually, or roughly 3 inches. These movements are not uniform across the entire caldera, but instead occur in localized regions, reflecting variations in pressure within different parts of the underlying system. With the updated multi-level magma framework, these deformation patterns can be interpreted with greater specificity. Uplift episodes are often linked to the accumulation of fluids or magma in mid-crustal storage zones, typically at depths of around 8 to 12 kilometers or approximately 5 to 7 miles. However, the recognition of shallower melt-bearing regions introduces an additional layer of interaction. Pressure changes in deeper zones can propagate upward, influencing the behavior of the shallower mush regions. Conversely, changes in the shallow system, particularly involving hydrothermal fluids, can modulate how deformation is expressed at the surface. This interconnected behavior complicates the interpretation of signals that might otherwise appear straightforward. A period of uplift, for example, does not necessarily indicate magma moving closer to the surface in a direct sense. It may instead reflect the pressurization of fluids within porous rock, the expansion of gases, or the redistribution of melt within an existing storage zone. The improved imaging helps to separate these possibilities by providing a clearer map of where melt is actually present and how it is distributed vertically. Another aspect gaining attention is the role of permeability within the crust. The ability of fluids and gases to move through rock depends on the presence of fractures and pore spaces, which can open and close in response to stress. In regions where shallow melt exists at depths of 2 to 4 kilometers, or about 1 to 2.5 miles, the surrounding rocks are often near the threshold where small changes in pressure can significantly alter permeability. This creates a feedback system in which fluid movement affects pressure, and pressure changes in turn affect fluid pathways. Gas emissions, particularly carbon dioxide and sulfur-bearing compounds, provide another window into these processes. These gases originate from magma at depth and migrate upward through the crust, sometimes dissolving in groundwater before being released at the surface. Variations in gas flux can indicate changes in the underlying system, but interpreting these variations requires careful consideration of both magmatic and hydrothermal influences. A spike in gas emissions does not automatically imply new magma rising. It may instead reflect the opening of new pathways that allow previously trapped gases to escape more efficiently. Thermal output across Yellowstone's geothermal regions also reflects the influence of the underlying magma system. The total heat flow from the region is immense, estimated at several gigawatts, equivalent to the energy output of multiple large power plants. This heat is not delivered uniformly, but is concentrated in areas where water circulates deeply enough to be heated by rocks close to or within melt-bearing zones. Changes in the distribution of shallow melt can subtly alter these regions, shifting where heat is most intensely expressed at the surface. One of the more significant implications of the updated model involves the concept of connectivity. For an eruption to occur, isolated pockets of melt must become sufficiently connected to allow large volumes of magma to move coherently toward the surface. The current understanding suggests that while melt exists in multiple zones, these regions are not presently connected in a way that would support large-scale movement. The melt fractions, ranging from approximately 6% to 28%, indicate that much of the system remains dominated by solid material. In such conditions, magma movement is hindered, and the likelihood of rapid ascent is reduced. Seismic monitoring continues to play a central role in assessing this connectivity. Low-frequency earthquakes, often associated with fluid movement, can provide clues about the state of the system. These events differ from typical brittle fracture earthquakes in that they often indicate the movement of liquid rather than the sudden fracture of rock. While such signals are occasionally detected beneath Yellowstone, they have not shown a sustained pattern indicative of increasing connection between melt zones at shallow depths. The time dimension remains critical in understanding Yellowstone's behavior. Geological processes operate over timescales that extend far beyond human observation. The current configuration of the magma system is the result of processes that have unfolded over hundreds of thousands of years. The last major eruptive event at Yellowstone occurred approximately 640,000 years ago, with smaller events occurring more recently on geological timescales. The presence of shallow melt today must be viewed within this long-term context, where periods of relative stability can persist for tens of thousands of years. At the same time, the ability to detect and monitor subtle changes has improved dramatically in recent decades. Networks of seismic stations, satellite observations, and ground measurements provide continuous streams of data, allowing for near real-time analysis of the system. This constant monitoring ensures that any significant deviation from established patterns would be detected promptly. The challenge lies not in the absence of data, but in its interpretation, particularly when new findings reshape the baseline understanding of the system. The integration of the 2025 research published in journals such as Nature has been instrumental in advancing this understanding. By combining high-resolution seismic data with other geophysical methods, these studies have demonstrated that Yellowstone's magma system is neither static nor simple. It is a layered, evolving structure in which melt is distributed across multiple depths, influenced by both deep mantle processes and shallow crustal conditions. This refined model also has implications beyond Yellowstone itself. Similar approaches are being applied to other volcanic systems around the world, revealing that multi-level storage and partial melt are common features rather than exceptions. The idea of a single large magma chamber is increasingly being replaced by models that emphasize distributed storage and complex connectivity. Yellowstone, with its extensive monitoring infrastructure, serves as a key site for developing and testing these ideas. Public perception, however, often lags behind scientific understanding. The phrase "magma detected closer than ever" can be interpreted as an indication of imminent danger, particularly given Yellowstone's reputation as a supervolcano. In reality, the detection of shallow melt is a reflection of improved resolution rather than a sudden change in the system's state. It underscores the importance of precise language in communicating scientific findings, especially when those findings relate to natural hazards. Risk assessment frameworks incorporate this evolving understanding by focusing on measurable indicators such as deformation rates, seismic activity, gas emissions, and thermal changes. Each of these factors contributes to an overall picture of the system's state. The presence of shallow melt is one component of that picture, but it must be considered alongside other data to assess the likelihood of future activity. At present, these indicators do not collectively suggest an increased probability of eruption. Nonetheless, the continuous refinement of subsurface models ensures that any future changes will be interpreted within a more accurate framework. As imaging techniques continue to improve, it is likely that even finer details of the magma system will be revealed, potentially identifying smaller melt pockets or transient features that were previously undetectable. These advancements will further enhance the ability to distinguish between background variability and meaningful shifts in the system's behavior. If you found this deep dive into Yellowstone's hidden system informative and engaging, make sure to like, share and subscribe for more detailed updates on the most closely watched geological systems on Earth. Don't forget to tap that hype icon to help this video reach a wider audience and keep bringing more in-depth coverage straight to you.